So in this video we're going to talk about whether a quadratic function has an inverse. So here's the quadratic toolbox function, which we're going to use as our example for this conversation. And remember, we said that to find an inverse relationship, if we have a graph, that we take the graph for which we are interested in finding the inverse, and we have to reflect that graph in the line y equal x. Reflecting in the line y equal x takes the x's and makes them become y's, and takes the y's and makes them become x's. It switches the inputs and the outputs. So if I take this quadratic function x squared and I reflect it in the line y equal x, it kind of immediately becomes apparent what the big issue is. The issue is that the relationship that we wind up with, this reflected relationship here, clearly doesn't pass the vertical line test. It's clearly not a function. In fact, we can actually apply a horizontal line test. So if we can draw a horizontal line through a function, and that horizontal line intersects in two places, what we know or can recognize is that when we reflect the function in the line y equal x, that, see, here's a 4, that 4 gets reflected down here, and now what didn't pass a horizontal line test now becomes something that can't pass a vertical line test. So a quick check to see whether a function has an inverse function, is to draw horizontal lines through it. If they intersect in more than one spot, then you know that the reflection of that function, the relation that you get when you reflect it, that it's not going to pass the vertical line test. So the question is there anything that we can do about it? Well, think about what an inverse is, right? So inverse means solve for the input variable. So solve for x in this particular case. So to do that, we would have to take the square root of both sides. And if we took the square root of x squared, we would get x. But because we took the square root of both sides, we would have a plus or minus right here. So the idea is that the positive square root actually corresponds to the top or upper half of that reflection, and the negative square root's actually corresponding to the lower half of that reflection. So if we turn off the reflection that we made, we can actually look at this as restricting the what we call a domain restriction, or restricting the domain. So what if we consider y equal x squared, but we restrict the domain? We say only let x start at 0 and go to infinity. In other words, only look at the input axis starting at 0 and going towards infinity, or throw this part of the graph away. So if we throw the part of the graph away that's to the left of the line of symmetry, here's what you wind up getting. You get doesn't look like it's wanting to because I don't come here, turn, there we go. So if we throw away the left half of that parabola, now we get something that does pass a horizontal line test. See, we're only looking at it with x an element of the interval from 0 to infinity, and we can see that the range, because the arrow goes up here, the range is actually starting at 0 and going to infinity. So the y's are going from 0 to infinity as well. And then if we reflect just this half in the line y equal x, we do get a reflection that passes the vertical line test. So it's a function. So this is called restricting the domain. So if I restrict the domain on x squared and I say only use x on the interval from 0 to infinity, and the outputs there go from 0 to infinity as well, then I can use the x equals the square root of y. And that would be this reflection right here. If instead we restrict the domain like this, we say let the domain be, let's let x run from negative infinity all the way up to and including the 0. So in other words, get the pin back. In other words, only look at the part of the parabola that lives from 0 to negative infinity. So that means turn off the right half of the parabola, the part that's to the right of the line of symmetry, and turn on the part of it that is to the left of the line of symmetry. And then if we reflect this in the line y equal x, we'll get something that is a function that passes the vertical line test. So if we restrict the domain and we say, hey, let's still keep y equal x squared, but only let's look at it from x going from negative infinity up to 0 so that we get this half, which means the outputs, I hate having to switch back and forth between the pins. The range on y equal x, squared, if we do this, is still going to be y going from 0 to infinity. So 0 to infinity. If we do that, then we get the reflection that is is underneath the x-axis, and this is actually the equation x equals the opposite of the square root of y when we solved this and got that plus or minus y on it. So we can get an inverse for a quadratic function, but only if we restrict the domain so that what's left of the original parabola passes a horizontal line test, so that its reflection in the line y equals x will pass a vertical line test.